Welcome to the deep dive. Today, we're jumping right into the next big thing in sequence modeling for AI. We're looking beyond transformers, even exploring these models that are really making waves because they're efficient and can handle just enormous sequences.
Exactly. Structured state space models, or SSMs. If you're keeping an eye on AI research, these are, well, pretty critical right now. It's not just tinkering, it's a genuinely different way of thinking about sequential data.
And we're using a fantastic source for this, from S4 to Mamba, a comprehensive survey on structured state space models. It literally just came out March 2025. So think of this as your fast track, getting up to speed on these cutting edge ideas without digging through piles of papers.
Yeah, a really comprehensive look.
So our mission today is basically to unpatch the key innovations, understand the academic weight behind these SSMs, and see exactly how they're solving problems that older models, well, struggled with.
Okay, so maybe before we get into the weeds with SSMs, let's quickly remind ourselves why people were even looking past RNNs and transformers. What were the big hurdles?
Right. Good starting point. RNNs, recurrent neural networks, they seemed neat conceptually, this looping state, but they're hit real problems with longer sequences.
The classic vanishing and exploding gradients issue, yeah.
Exactly that. Made it super hard to remember stuff from way back in the sequence. Plus, they had to process things one step at a time, sequentially. So forget about massive parallel processing power.
Which was a major bottleneck for scaling them up. Okay, so then transformers arrived. Big dupe forward, especially with self-attention capturing those global links. But they weren't perfect either, were they?
No, definitely not. The elephant in the room was the quadratic complexity, both time and memory scaled with the square of the sequence length.
In squared, yeah.
So if you double the sequence length, you quadruple the compute cost, roughly speaking. Made them really hungry for resources on very long inputs. And they also had those fixed positional embeddings, which wasn't always ideal.
Okay, so that sets the stage nicely for structured state space models. What's the fundamental difference in their approach, and what are the big advantages they're bringing?
Right, so SSMs come at it from a totally different angle, mathematically. It's based on state space representations, borrowing ideas from control theory, but adapting them heavily for deep learning.
And the big headline?
The big headline is efficiency. They aim for linear or maybe near linear complexity like ON plus L instead of that quadratic scaling.
Which is a massive difference for long sequences.
Huge. It opens the door to processing things like, entire books, maybe long video streams in one go, stuff that was just computationally infeasible before. They also seem much better at holding on to long-term dependencies, fixing that RNN problem, and importantly, they can be parallelized effectively.
Now, you mentioned control theory. It's probably worth clarifying the difference between those classical state space models and these new structured SSMs for deep learning.
Yeah, good point. Classical SSMs are veterans in fields like engineering, modeling, physical systems. They usually use constant matrices parameters that don't change. Structured SSMs are built for sequence modeling in AI. Their parameters are learned from data, and they have specific structures, often involving things like diagonal matrices or special initializations that make them work well for learning complex patterns in sequences.
So learned parameters and tailored structures for AI tasks. Makes sense. The survey mentions two main ways to think about how these discrete time SSMs compute things. What are those?
Okay, yeah. First, there's the recurrent view. You can think of it like updating a hidden state step by step, a bit like an RNN, but with a different underlying math and structure.
And that's good for
Things where you need that memory, with autoregressive tasks generating text one word at a time for analysis. And the specific structure helps gradients flow better during training, avoiding some of those old RNN issues.
Okay, and the second view?
Second is the convolutional view. Instead of step-by-step, you calculate a kind of filter or kernel based on the SSM parameters, and then you apply that filter across the entire input sequence at once, like a CNN, a convolutional neural network.
Ah, so that's where the parallelization really kicks in.
Exactly. Great for parallel hardware like GPUs. You can do the whole sequence calculation much faster for training and inference. And what's neat, academically speaking, is that this isn't just a fixed filter like in a standard CNN. It's derived from these learned state space parameters, giving it flexibility for long-range patterns.
That dual nature, recurrent and convolutional from the same core math, is pretty fascinating. Shows their versatility. Okay, so the survey points to S4 as a real trailblazer here. What were its key breakthroughs?
S4 really was the first model specifically designed as a structured SSM to beat the long sequence limitations of RNNs and transformers. The absolute core innovation was something called the high PPO framework, high order polynomial projection operator.
High PPO. Catchy name. What's the idea behind it? How did it help with long memory?
So, HiPO at its heart is a mathematically clever way to approximate a function's history online. Think of it like continuously summarizing a long stream of information into a compact representation using polynomial bases. It allows the model to effectively remember relevant information from far back without needing infinite memory.
Okay, like a sophisticated compression technique for the sequence history. And S4 built this into its state space structure.
Precisely. S4 used these HiPO-inspired structures for its state matrices. This allowed it to take the continuous time idea and dispertize it into these very efficient convolutions we just talked about. So you get the speed of parallel convolutions, but they implicitly capture long-range dependencies because of the underlying HiPO math. Best of both worlds, kind of.
The survey also mentions a specific structure, diagonal plus low-rank parameterization. Why is that particular structure significant from, say, an academic or a computational viewpoint?
Right. That structure is key for making S4 practical. The diagonal part makes the math stable and efficient, easy to compute in parallel on hardware. The low rank part adds back some expressive power, letting it model complex patterns without making the matrices huge and slow. It's this really elegant trade-off between computational efficiency and modeling capacity.
And complexity-wise, how much better was S4 than the transformers?
It brought it down significantly. Depending on the exact implementation, it was O(n) log n, or sometimes O(n) log n. That subquadratic scaling was a huge deal for really long sequences where n just becomes too costly.
Makes sense. So where did S4 show its strengths? What kind of applications?
It did well in several challenging areas. NLP, especially with long documents, time series analysis, picking up complex patterns over time, and even biomedical signals like analyzing EEG brainwaves or ECG heart data, which can be very long and noisy sequences.
Sounds like a really important step. Did it have any downsides or challenges?
Yeah, nothing's perfect. The main thing mentioned is that getting S4 to train well often required pretty complex initialization techniques. You couldn't just randomly start the parameters. You needed specific methods like spectral normalization to get things going stably. So a bit more complex to implement initially.
Okay, let's dig a bit deeper into those core academic innovations of S4 you mentioned. First, that structured recurrence from the state space math. How exactly does that structure help maintain long-range dependencies? Can you maybe connect it to the actual state space equations?
Sure. Remember the basic continuous time equations like E equals x plus b and y equals cx plus do. The state x evolves based on its current value via matrix A and the input u via matrix B. The output y depends on the state via C and input via D.
Right.
In S4, the crucial point is that A, B, and C aren't just learned freely. They have a specific mathematical structure, often derived from HiPO principles. This structure imposes a kind of continuity or smoothness on how the state evolves. It inherently links the state's evolution over time, meaning information from the past is naturally incorporated into the present state in a structured way. Even when you discretize this for the computer, that underlying temporal relationship persists. It prevents the memory decay you see in vanilla RNNs. If you look at Figure 4 in the survey, it shows how an S4 layer uses these parallel independent SSMs.
So the structure itself enforces a better memory. Okay. And the second big innovation, replacing sequential updates with efficient convolutions. How did that move improve both speed and the way dependencies are handled?
Yeah, this was a major conceptual shift. Instead of stepping through the sequence, S4 learns this special convolutional filter derived directly from those structured A, B, C matrices. Applying this one filter across the whole sequence in parallel is way faster, thanks to how well convolutions run on GPUs.
And the dependency part.
Because the filter itself is born from the state space math, which has that HiPO-inspired long memory property, the convolution inherently captures long-range patterns. It's like learning a single, very long pattern detector that efficiently scans the entire input at once, rather than trying to pass messages sequentially down the line like an RNN.
Got it. And the third piece you mentioned was FFT acceleration, fast Fourier transform. How did that fit in?
Right, that was the computational magic trick. Convolution in the time domain can still be costly for very long sequences, but if you switch to the frequency domain using the FFT, the convolution becomes element-wise multiplication, which is much faster, specifically O(n) log n fast.
Ah, the classic signal processing speedup.
Exactly. And FFT algorithms are super optimized for parallel hardware. So using FFTs to perform the S4 convolution made it dramatically faster and more scalable, especially on GPUs and TPUs. It was key to unlocking that subquadratic performance in practice.
Okay, so S4 laid this incredible groundwork. Now let's move to Mamba, which the survey calls a selective state space model. What are the key steps forward Mamba took, building on S4?
Mamba took the core S4 ideas and really focused on optimization and, crucially, selection. Its big innovations are this data-dependent selection mechanism and a very hardware-aware algorithm design. Together, these push the efficiencies even further, achieving true linear time complexity, OL, in many cases.
Linear time, wow, that's a huge goal. Let's unpack that data-dependent selection. How does that differ from S4 and what does it enable?
So in S4, the state space matrices, A, B, C, were generally fixed for a given input sequence once learned. Mamba makes these parameters dynamic. They can change based on the input data itself as it's being processed.
So it adapts on the fly.
Exactly. It has the selection mechanism that kind of filters the input, deciding what information is important to update the state with at each step. This allows it to selectively focus on relevant parts of the sequence history and ignore irrelevant stuff, which turns out to be really powerful for modeling extremely long dependencies even more effectively than S4.
And the hardware-aware part, what does that mean in practice?
It means Mamba's algorithms were designed specifically with the way modern GPUs work in mind. Things like optimizing how data moves between different levels of memory, like SRAM and HBM, reducing slow memory rewrites, using techniques like kernel fusion to combine multiple computations into one GPU step, and parallel scan algorithms. It's about minimizing computational waste by understanding the hardware bottlenecks. This careful co-design was critical for its speed.
Makes sense designing the algorithm for the silicon. The survey also mentions Mamba's gated state space model, GSSM, and the selective scan algorithm. How do those fit in?
The gated SSM part is related to that selection idea. It uses input-dependent gates, a bit like gates in LSTMs or GRUs, but integrated into the SSM framework. These gates control the flow of information, what gets passed through, what gets updated, what gets forgotten, allowing for more fine-grained control over the state dynamics.
And the selective scan.
The collective scan algorithm is a specific computational technique they developed to implement the recurrent mode of the SSM efficiently on GPUs, especially handling that data dependency we talked about. It optimizes the memory usage during the scan operation, making training faster and more memory efficient.
And the payoff was pretty substantial, right? Something like a 5x speed up in generation.
Yeah, the reported mains and throughput for autoregressive generation were really impressive. It showed these architectural improvements weren't just theoretical. And it didn't stop there. The survey shows how Mamba's core ideas are now spreading out into specialized areas. What are some examples?
It's really cool to see how adaptable these concepts are. Take Graph Mamba. It applies Mamba's principles to graph data, which is usually tricky because of irregular connections. It helps model long-range interactions within graph sequences, and apparently does so with less GPU memory than some existing graph neural network methods. Figure 5 in the survey gives a visual.
Okay, so graphs. What about more standard sequences like time series?
For that, there's Mamba TS. It's tailored for time series forecasting, focusing on those long-term temporal patterns. It uses a technique called variable scan along time, or VST, specifically to boost its ability to capture dependencies over extended periods. Figure 6 shows that one.
Interesting. And it's even breaking into vision, right? Image processing.
Yep. UMamba is a hybrid model. It slots Mamba blocks into the well-known UNet architecture, which is popular for things like medical image segmentation.
So combining the local feature power of CNNs with the global context handling of Mamba.
Exactly, trying to get the best of both worlds for image analysis. And then there's Fusion Mamba.
What's its focus?
That one tackles multimodal image fusion, combining information from different image sources, say visible light and infrared. It uses Mamba to help dynamically enhance and integrate features from the different modalities better. That's figure 8 in the survey.
Wow, okay, so Mamba's influence is definitely spreading. The survey also lists a whole bunch of other S4 variants and related hybrid models. Maybe we can quickly touch on a few more just to show the sheer breadth of activity here.
For sure, it's a rapidly evolving space. There's S5 simplified state space layers. It's a multi-input, multi-output version aiming for even better parallelism than S4, using a parallel scan on a diagonalized SSM structure. Figure 7 illustrates that.
And the hybrid trend seems really strong too.
Definitely. Jamba is a big one. It mixes transformer layers and Mamba layers, and even throws in mixture of experts, or MOE. The goal is efficiency and scalability for handling incredibly long context. They mentioned 256,000 tokens.
250,000 tokens, wow. Are there also efforts to simplify S4 itself?
Yes. DSSS, diagonal state spaces, just restricts the main state matrix to be diagonal, much simpler computationally. Then you have things like Liquid S4, which makes the state transitions sensitive to the input, potentially better for variable dependencies. And hyena, that's an interesting one that tries to replace self-attention entirely with long convolutions in gating, aiming for that subquadratic complexity.
We should probably also mention RWKV, right? That recurrent model that acts like a transformer.
Yeah, RWKV gets attention because it mimics transformer performance, but with constant memory use during inference and parallelizable training, which is quite unique for a recurrent setup.
And the list goes on.
It really does. S4ND extends S4 to multiple dimensions for images video using ideas from partial differential equations. Mega combines attention with exponential moving averages. S4D takes the simpler DSS and adds S4-style initialization for better stability. Mamba brings in Kalman filtering for reinforcement learning. Symbia adapts Mamba for vision and multivariate time series. It's just a huge amount of innovation happening very quickly.
It really underscores how fertile this ground is for research. Beyond these S4 Mamba descendants, the survey briefly mentions other categories too.
Just quickly, yeah, it drapes some others. There are other recurrent SSMs beyond RWKV, like linear recurrent units, LRUs, designed for parallel training and low memory, or hierarchical graph recurrent networks, HGRNs, for multi-agent systems. And then there's a category of gated and hybrid SSMs beyond Mamba and Jamba, like the basic gated state space, GSS, Mega, which we mentioned, and even Toplet's neural networks, TNNs, using special structured matrices for efficiency.
It's clear, looking at all this, that SSMs are just a massive area of focus right now, academically and potentially practically too.
Without a doubt.
Okay, so wrapping up our deep dive here, we've journeyed from the limitations of older models like RNNs and transformers through the foundational work of S4 and into the really exciting developments around Mamba and all these diverse spin-offs. It's definitely a major shift in how we approach sequence modeling.
Absolutely. The core takeaway is that these models offer new, often much more efficient ways to handle long sequences and capture those crucial long-range dependencies, tackling problems that were serious bottlenecks before.
And the sheer inventiveness is striking. The selective mechanisms in Mamba, the hardware co-design, the hybridization with transformers and CNNs. It really shows a field that's buzzing with new ideas and academic energy.
And hopefully for you listening in, this dive gave you a solid, clear picture of these important advancements and why they matter in the AI research landscape without getting lost in, excessive jargon.
So maybe a final thought to leave you with. As this research keeps accelerating, how might these super efficient, scalable SSM architectures fundamentally change AI applications? Think beyond just leaderboards. What happens when analyzing whole genomes becomes routine? Or modeling decades of climate data? Or building real-time systems that can understand conversations with massive context? The potential impact could be truly transformative across science and technology.
Yeah, it's exciting to think about. And of course, if you want to go even deeper, the survey paper itself is packed with more details and references for further reading.
That brings us to the end of this deep dive. Thanks for tuning in as we explored the cutting edge of sequence modeling.